Good morning. Today we will learn about work. You might have heard about this word in our daily life. What is the meaning of work in physics? And what is the difference from the daily life? In physics, work is said to be done when the point of application of force changes position. You might have heard about work in smaller classes, work done, force and displacement. Yes, it is true. We can measure work by multiplying force and displacement. Therefore, normally we will write W is equal to Fs, force into displacement. The SI unit of work is Joule. In CJ system, we are using ergs. Look at these two pictures, A and B. Whether they were doing work, let us analyze both these pictures. In the first picture, you can see is pushing, but the wall is not moving. Of course, in daily life, we can say he is doing work. But when it is coming to physics, we will say he is not doing any work. Work done is zero. Why? Because the point of application of force is not changing position. The displacement is zero. We know the formula W is equal to Fs. If S is zero, work done is zero. But in the case of second picture, we can see the body is moving. The body is doing work. Just imagine if the force and displacement are in a plane making an angle theta, whether the work done is same as before, force and displacement. No. Here in this case, the total force is not in the direction of displacement. A part of the force, we can say a component of the force, is only acting in the direction of displacement. We know along the horizontal direction, otherwise we can say along the theta direction, the component is cos. So F cos theta component, F after the force F cos theta is only acting in the horizontal direction. Therefore we can write work done W is equal to F cos theta into S. That is Fs cos theta. But we studied Fs cos theta, it is a product of two vectors. It is a scalar product of two vectors. Otherwise, you can say dot product of two vectors, force and displacement. Therefore, we came to know that force and displacement, the scalar product gives work done. Work is a scalar physical quantity. You can see here, a person is pulling the lawn mower. They shown the direction of force and the direction of motion. It is with an angle. Therefore, like these cases when it is coming in physics, when we are calculating work, we will use the general formula Fs cos theta. Now, just again think, see this picture here. A body is applied by a force F, and the body has got a displacement S. What about the work done? Here, the force and displacement are in the same direction. Therefore, W is equal to Fs cos theta. It is angle between force and displacement. That is zero. Therefore, work done W is equal to Fs cos 0. We know cos 0 is equal to 1. Therefore, W is equal to Fs. Here in this case, we can say work done is positive. Now look here. Does the centripetal force do work? We know in this figure we can see a person is throwing the hammer. Before throwing, he will rotate the hammer and he will release. And we know the hammer will move along the tangent of the circle. When he is rotating, whether he is doing any work in physics, here the force is inverse and the displacement along the tangent. The angle between force and displacement is 90 degree. Cos 90 is equal to 0. Therefore, work done is 0. Look at these pictures here. A person is carrying a bucket of water. He is lifting. His lifting force is in the upward direction, and the bucket is moving in a horizontal direction. Similarly, a person carrying a load on his head. What about work done by the lifting force or work done with the gravitational force in the second figure? We can see in both figures work done by the lifting force is zero. Why? Force and displacement are perpendicular to each other. Angle between force and displacement is 90 degrees. Therefore, work done W is equal to Fs cos 90 is equal to 0. Again, the second figure, work done against the gravitational force, is applying the force in the upward direction and the body is moving along the horizontal direction. Here also, work done is 0. Force and displacement are perpendicular to each other. Just look this case. Just imagine a person is lifting a bucket of water and is climbing a staircase. We know gravitational force is downward and the displacement is in the upward direction. What about the angle between force and displacement? It is 180 degree. Therefore, force into displacement. Fs cos 180. Cos 180 is equal to minus 1. Therefore, work done is negative. Therefore, in physics, we can say work can be positive, work can be negative, work can be 0. Now, here in the section, we will discuss about work done by constant force. The force is constant, same force is applied, and the displacement is there on the body. We can calculate force into displacement gives the work done. Work done W is equal to Fs. If you are drawing in a graph force and displacement, we'll get a graph like this. The graph will be parallel to displacement axis. Force always constant. Consider 2 points and drop the perpendiculars from the points to the displacement axis. We'll get a rectangle. We can calculate the area of the rectangle, length into breadth. On one side, force, other side, displacement. Therefore, work done is equal to Fs. Therefore, from this, we know that if work done by a constant force, The force displacement graph will be a straight line parallel to displacement axis. And when you are calculating the area under the first graph, force displacement graph, we will get the work done. Now just look here, the case of a uniform variable force. Force is uniformly vary. What will be the nature of the first graph we are going to get? From the figure we know, if the force is uniformly varying, the force displacement graph will be a straight line with a slope. And how we can find out the work done? Again, it is area under the graph. Therefore, when you calculate the area, we'll get a triangle there and half base into altitude. From that formula, we are able to calculate the work done. Now look this case, general case, work done by a variable force, not uniformly variable force. It is a variable force, non-uniformly variable force. Whether we will get a straight line? No. If you are drawing a graph between force and displacement, we will get a graph, a curve, as seen in the figure. How we can calculate the area? Therefore, we have to adopt some mathematical approach. We are dividing these curves into small pieces of delta x thickness each. And we are making it into small pieces in such a way that each piece is almost similar to one rectangle. Area of that small piece is equal to, we can say, delta A force into a small displacement delta x. I already said we are dividing in small pieces in such a way that we can say the breadth on the upper side is almost a straight line. That means force remains constant in that small interval delta x. Therefore, we are calculating the area of that small rectangle, force into displacement. How we can calculate the total area? We have to sum up these small areas. We can write total work done is the total areas of, we can say, sigma I is equal to 1 to n fi delta xi, we can say. If the delta x is tending to 0, limit delta x tending to 0, sigma I is equal to 1 to 0, 1 to n fi delta x. Mathematically, we write like this: integral xi to xf, otherwise x1 to xn, f of x dx. So, this is the formula. W is equal to integral x1 to x2 of x dx, xi to xf. If initial point is xi and final point is xf, we can write integral xi to xf, f of x dx. This xi and xf, we'll see limits of integration in mathematics. Here we know there is a initial displacement and final displacement. But this is a general formula work for a work done by a variable force. W is equal to integral xi to xf of x dx. Thank you. We will see in the next class.